March 9, 1945. Remagen, Germany. The morning air still carried the acrid smell of explosives and burning timber from the previous night's artillery barrage. In a requisitioned farmhouse 3 kilometers east of the Rhine, a team of Luftwaffe radar specialists gathered around a prize that had fallen into their hands through the chaos of the American advance. An intact SCR-584 mobile radar system, captured when its crew abandoned it during a hasty retreat across the Luttendorf Bridge. The equipment sat in the barn, still mounted on its trailer, its dish antenna pointing skyward like a mechanical flower turned toward an invisible sun. Oberleutnant Werner Hartmann, a graduate of the Technical University of Berlin and a veteran of radar development since 1940, approached the American system with the careful reverence of a man about to examine something he both feared and needed to understand. The metal housing was dented from transport, splattered with mud from German roads, but the equipment itself appeared undamaged. Hartmann's gloved hand traced the smoothly machined surfaces of the rotating assembly, felt the precision of the bearings, noted the compact arrangement of components that seemed to fit together with an elegance his own equipment rarely achieved. Around him, 3 other specialists began documenting the system with cameras and measurement tools, working quickly because everyone understood that within hours or days, the Americans would recapture this ground, and this window of opportunity would close forever. But even in those first moments of examination, before a single cover plate had been removed or a single circuit analyzed, Hartmann felt a cold certainty settling in his chest, a recognition that what lay before him represented not merely a different approach to radar technology, but evidence of an industrial and scientific capability that Germany, for all its vaunted technical superiority, had failed to match.
He opened the equipment housing. Inside, arranged with almost mathematical precision, lay the components of what American forces called their automatic tracking system, the technological backbone of an anti-aircraft fire control network that was destroying German aircraft with efficiency that Luftwaffe intelligence had initially dismissed as impossible. The reports from the field had been consistent and troubling. American anti-aircraft batteries were hitting targets in darkness, through cloud cover, at ranges where visual tracking should have been impossible. German bomber crews reported being bracketed by flak with uncanny accuracy, shells exploding in patterns that suggested the Americans somehow knew exactly where the aircraft would be seconds before it arrived there. The standard explanation, that American gunners were simply better trained or luckier, had become untenable when squadron after squadron returned with the same story, when loss rates to anti-aircraft fire climbed to levels that made certain mission profiles unsustainable. Now, looking at the SCR-584's interior, Hartmann began to understand why. This was not simply a radar that detected aircraft. This was a system that tracked them automatically, calculated their trajectory, computed firing solutions, and transmitted that data directly to gun directors without requiring manual intervention. It was, in essence, a mechanical brain that had rendered obsolete the entire German approach to anti-aircraft fire control.
To understand the magnitude of what Hartmann's team discovered that morning, one must first understand the trajectory of radar development during the war and the fundamentally different paths taken by German and American engineers. Germany had been a pioneer in radar technology. The Würzburg radar, developed in the late 1930s, had given the Luftwaffe the ability to detect incoming bombers at ranges of up to 40 kilometers. German engineers had refined this technology throughout the early war years, creating variants like the Würzburg Ries with its 7.5-meter dish that could detect aircraft at 70 kilometers. These were remarkable achievements, representing the cutting edge of radio frequency engineering. But German radar development had followed a path dictated by military doctrine and industrial constraints. Each radar system was designed for a specific purpose, the Freya for long-range early warning, the Würzburg for gun-laying and fighter direction, the Liechtenstein for airborne interception. Each system was operated by trained specialists who interpreted the radar returns and manually communicated that information to gun crews or fighter pilots. The systems were effective within their designed parameters, but they were fundamentally passive. They detected and reported, but the loop from detection to action still required human intervention at multiple stages. The Americans, entering radar development later, but with the full resources of their industrial base and scientific establishment, had approached the problem differently. The Radiation Laboratory at MIT, established in 1940, had brought together physicists, engineers, and mathematicians with a mandate to create not just radar systems, but integrated fire control solutions. The SCR-584, which emerged from this effort in 1943, represented a philosophical departure from previous radar design. It was not merely a detection device, but an automatic tracking and fire control computer that used analog circuits to continuously calculate target position, velocity, and predicted future location. The technical specifications were remarkable. The SCR-584 operated at a frequency of 3,000 MHz, far higher than most German systems, which meant shorter wavelengths and greater precision. Its dish antenna, just over 2 meters in diameter, rotated at speeds up to 40 revolutions per minute, maintaining continuous lock on targets, moving at speeds up to 500 miles per hour. But the revolutionary feature was the automatic tracking mechanism. Once the radar operator designated a target, the system locked onto it electronically and followed it without further manual input, continuously updating position data and transmitting that information to the M9 gun director, which automatically calculated firing solutions and adjusted gun positions. This integration, radar detection flowing seamlessly into automated tracking, flowing seamlessly into computed fire control, created a response loop measured in seconds rather than the minutes required by manual systems. An American anti-aircraft battery equipped with SCR-584 and M9 directors could engage targets within 15 seconds of detection with accuracy that approached theoretical limits regardless of visibility conditions.
Werner Hartmann spent 3 days examining the captured SCR-584, working with an urgency born of desperation. He and his team carefully dismantled components, sketched circuit layouts, measured signal characteristics, and documented every aspect of the system's design. What they found was both impressive and deeply troubling. The American radar used cavity magnetrons that generated microwave frequencies with power outputs German equipment could not match. The tracking circuits employed feedback loops and servo mechanisms of elegant sophistication. The power supplies were compact and reliable. The entire system was designed for mass production. Standardized components, modular construction, simplified maintenance procedures. But it was not any single technical feature that most disturbed Hartmann. It was the integrated nature of the entire system, the evidence of coordinated development between radar manufacturers, computing equipment designers, and artillery specialists. The SCR-584 had clearly been designed as part of a larger ecosystem of fire control equipment. It spoke to data links in standardized formats. It anticipated integration with automated gun directors. It assumed an infrastructure of technical support and trained operators. This level of coordination required something Germany had never achieved: genuine cooperation between military services, industrial manufacturers, and academic researchers, all working toward a common technical standard. German radar development, by contrast, had been fragmented across multiple organizations: Luftwaffe research facilities, Kriegsmarine laboratories, Army ordnance departments, private manufacturers like Telefunken and Siemens, each pursuing their own designs, often duplicating effort, rarely sharing information freely. The result was a collection of capable individual systems that could not easily work together and could not be mass-produced with the efficiency the war demanded. Hartmann's preliminary report, rushed to Luftwaffe headquarters on March 12, made for grim reading.
The American SCR-584 represents not merely an advancement in radar technology, but a fundamental reorganization of the fire control problem, he wrote. Where our systems require skilled operators to manually track targets and communicate data through voice circuits to gun positions, the American system automates the entire process, from detection through fire control. The implications for the effectiveness of enemy anti-aircraft defenses are severe. Our bomber formations can expect engagement by accurate fire regardless of visibility conditions, with response times that preclude effective evasion. What Hartmann understood, but could not explicitly state in a military report, was that the SCR-584 represented evidence of American scientific and industrial maturity that German propaganda had consistently denied. The official narrative had held that German technical education was superior, that German engineering discipline produced better results, that American science was shallow and derivative. But the system sitting in that farmhouse barn contradicted every element of that narrative. Here was equipment that represented years of focused development by highly skilled scientists working with essentially unlimited resources. Here was proof that American industry could not only design sophisticated electronics, but manufacture them in quantity. Over 1,400 SCR-584 systems would be produced by war's end, a number that exceeded total German production of all mobile radar types combined. The SCR-584's development history told its own story about American organizational capacity. The project had begun in early 1941 at the MIT Radiation Laboratory, where physicist Ivan Getting led a team tasked with creating an automatic tracking radar for anti-aircraft use. Getting's team built on earlier British research. The cavity magnetron technology that made microwave radar practical had been shared by British scientists in one of the war's most significant technology transfers. But the Americans had taken that foundation and built upon it with characteristic pragmatism and resource abundance. The development process involved parallel efforts in radar design, servo control systems, analog computing circuits, and power supply engineering. MIT coordinated with Bell Laboratories on fire control computers, with Western Electric on production engineering, with Chrysler Corporation on vehicle mounting systems. The Army's Signal Corps provided operational requirements and testing feedback. The entire effort, from initial concept to field deployment, took less than 2 years, a pace of development that German engineers, accustomed to years-long development cycles and constant resource shortages, would have considered impossible.
The first SCR-584 units reached American anti-aircraft batteries in Tunisia in late 1943. The results were immediate and dramatic. German bomber formations that had previously operated with relative impunity during night raids suddenly faced accurate fire regardless of visibility. The statistics were stark. American anti-aircraft batteries equipped with SCR-584 achieved hit rates 3 to 4 times higher than units using optical directors. Against V-1 flying bombs launched against Antwerp in late 1944, SCR-584 directed guns achieved an 89% destruction rate, a percentage so high that German intelligence initially dismissed it as Allied propaganda. But it was not propaganda. It was the consequence of integrating advanced radar with automated fire control, creating a system where human reaction time was removed from the engagement loop. The SCR-584 detected the incoming V-1, automatically tracked its trajectory, computed its future position, accounting for projectile flight time, and continuously updated gun positions to maintain predicted intercept. The entire process occurred faster and more accurately than any manual system could achieve. Werner Hartmann's detailed technical report, completed in late March as American forces pushed deeper into Germany, became one of the last comprehensive technical intelligence assessments produced by the Luftwaffe. In meticulous detail, it documented not just the SCR-584's capabilities, but the systematic advantages that had allowed its development. The report noted the high-quality components, the evidence of rigorous testing, the sophisticated understanding of radio frequency propagation and servo control theory.
But between the technical paragraphs lay a subtext that any careful reader would recognize. This is what coordinated national effort, backed by industrial capacity and scientific talent, can achieve. This is what we failed to create. German radar development had not been without its successes. The Wurzburg system had served effectively throughout the war. German scientists understood microwave theory and had conducted their own cavity magnetron research. But resource scarcity, organizational fragmentation, and constant pressure for immediate results had prevented the kind of long-term integrated development effort that produced the SCR-584. German engineers built systems that worked within existing doctrinal frameworks. American engineers, freed from immediate operational pressures by the breathing room that industrial capacity provided, reimagined the entire framework. This difference in approach extended beyond radar to encompass the entire spectrum of military technology. Germany had developed remarkable weapons, jet aircraft, ballistic missiles, infrared targeting systems, but these existed as isolated achievements, often competing for scarce resources, rarely integrated into coherent operational systems. America developed fewer revolutionary individual technologies, but integrated them into systems that worked reliably at scale. The SCR-584 was not the most advanced radar theoretically possible. It was the most advanced radar that could be manufactured in quantity, deployed to hundreds of batteries, operated by trained but not specialist personnel, and maintained in field conditions. This philosophy of good enough but available everywhere had defeated Germany's philosophy of technically superior but scarce. The lesson was evident in every theater of war. German Tigers were superior to American Shermans in armor and firepower, but America built 50,000 Shermans while Germany built 1,300 Tigers. German U-boats were sophisticated submarines, but American shipyards produced cargo vessels and escort carriers faster than submarines could sink them. German radar was technically proficient, but American radar achieved operational superiority through integration, automation, and scale. The SCR-584 that Werner Hartmann examined in March 1945 never made it to a German laboratory for deeper analysis. American forces recaptured Remagen before the system could be transported east, and Hartmann's team was forced to destroy what they could not carry and retreat only with their notes and photographs. Hartmann himself survived the war and found work in the radar industry of the Federal Republic of Germany, where many of the organizational principles that had created the SCR-584, cooperation between academic research, industrial production, and military requirements, were eventually adopted by NATO forces during the Cold War. In post-war interviews, Hartmann spoke carefully about his wartime experiences, constrained by the complicated politics of German memory and American occupation. But in a 1962 conversation with an American radar engineer visiting Siemens, where Hartmann had become a senior researcher, he allowed himself a moment of candor. They stood in a laboratory examining the latest air defense radar system, a product of NATO collaboration that combined American transistor technology with German manufacturing precision. "This is what we should have been building in 1943, Hartmann said, gesturing at the integrated fire control display. But to build this, we would have needed to admit that integration mattered more than individual technical excellence. We would have needed to coordinate across services and companies. We would have needed to think in terms of systems, not components. The Americans understood this. We did not, until it was too late." His American colleague, a former MIT radiation laboratory engineer who had worked on the SCR-584 project, nodded slowly. "You're being too hard on yourself. You built excellent components. What you didn't have was the luxury of time and resources to integrate them properly. We had that luxury because our factories weren't being bombed and our physicists weren't being conscripted to fight on the Eastern Front." Hartmann considered this charitable assessment, then shook his head slightly. "Perhaps, but I think the difference was more fundamental. Your system assumed that the technology served the operator, that automation should remove burden rather than require expertise. Our systems assumed that skilled operators would overcome technical limitations. One philosophy scales with mass production, the other depends on artisanship.
In total war, scale defeats artisanship. The sound that defined the SCR-584's presence on the battlefield was not the roar of its own operation. Radar systems are quiet machines, humming softly with electrical current, but the sound it enabled, the precise rhythmic thunder of anti-aircraft batteries firing in coordinated salvos, shells exploding in tight patterns around their targets. German air crews learned to recognize this sound, distinct from the random scatter of manually directed fire. It was the sound of mathematical certainty translated into explosive force, the atmospheric signature of automated fire control. This sound became a psychological weapon as effective as the physical destruction it represented. Bomber pilots who survived attacks by SCR-584 directed batteries reported a particular kind of terror, the sense of being hunted by an unhuman intelligence that never tired, never lost focus, never made the small errors of timing and prediction that human gunners inevitably made. The radar could not be evaded by traditional tactics. Changing altitude or course simply caused the system to recalculate. Darkness provided no concealment. Cloud cover offered no protection. The only effective defense was to avoid areas where SCR-584 batteries operated. But by 1944, those areas included virtually every strategically significant target in Western Europe. This psychological impact extended beyond individual aircrews to affect Luftwaffe operational planning. Mission profiles were modified to avoid predicted concentrations of automated fire control. Attack altitudes were raised to levels that reduced bombing accuracy because staying lower meant flying through zones where American radar-directed fire achieved near certainty of engagement. Resource allocation shifted towards night fighters and jet aircraft, technologies that promised to avoid anti-aircraft fire entirely, even as those programs diverted resources from conventional bomber production. This ripple effect, where one American technological advantage forced German responses that weakened other capabilities, illustrated how integrated systems could achieve strategic effects beyond their immediate tactical function. The SCR-584 did not win the air war by itself, but it contributed to an accumulation of technical advantages that made German air operations increasingly costly, eventually unsustainable, and ultimately irrelevant to the war's outcome.
By the time Werner Hartmann examined the captured SCR-584 in March 1945, the war's conclusion was no longer in doubt. Germany's cities were rubble, its industry shattered, its armies in retreat on all fronts. In this context, the discovery of American radar superiority might seem like merely another piece of bad news in an unending cascade of defeats. But for Hartmann and the small community of German scientists who understood what they were looking at, the SCR-584 represented something more significant than a tactical disadvantage. It represented proof of a hypothesis many had secretly suspected but could not openly acknowledge: that Germany had lost the technological race that Nazi propaganda claimed it was winning. This recognition carried implications that extended far beyond military technology. If American science could produce systems like the SCR-584, then the entire edifice of National Socialist claims about Aryan intellectual superiority and democratic decadence stood exposed as propaganda. The radar system in that farmhouse barn was not just evidence of better engineering. It was evidence of better organization, better education, better integration of theoretical science and practical application, better coordination between government, academia, and industry. It was evidence of a functioning scientific and industrial democracy that could outthink, out-innovate, and outproduce the totalitarian system that had promised efficiency through centralized control. Hartmann understood this even if he could not say it aloud in March 1945. He understood it more clearly in the years that followed, as German scientists and engineers were integrated into American and European research programs, as the mechanisms of democratic scientific organization were gradually explained and adopted, as the post-war economic miracle demonstrated what German talent could achieve when freed from ideological constraints and organizational dysfunction.
The SCR-584 had demonstrated that automated systems could outperform human operators in specific, well-defined tasks. But the system's development had demonstrated something more profound, that democratic societies, with their emphasis on collaboration, knowledge sharing, and pragmatic problem-solving, could organize complex technological development more effectively than authoritarian societies with their hierarchies, secrecy, and ideological rigidity.
In the final analysis, the story of the SCR-584 is not primarily a story about radar technology. It is a story about how societies organize knowledge and translate that knowledge into capability. The American radar system succeeded not because American scientists were inherently more intelligent than their German counterparts. Many German physicists and engineers were world-class talents, as their post-war careers would demonstrate, but because American institutional structures enabled them to work more effectively. The MIT Radiation Laboratory operated as a collaborative environment where physicists, engineers, and mathematicians worked in close proximity, sharing ideas freely, building on each other's insights without regard for disciplinary boundaries or proprietary concerns. Military requirements were communicated clearly and incorporated into design from the beginning. Industrial production capabilities were considered as part of the design process, not as an afterthought. Testing and feedback happened continuously, allowing rapid iteration and improvement. This organizational model, sometimes called systems engineering in later years, was not uniquely American, but America's particular combination of academic freedom, industrial capacity, and democratic culture made it particularly effective at implementing such approaches at scale. The same model that produced the SCR-584 also produced the proximity fuse, the Norden bomb sight, the atomic bomb, and dozens of other technological achievements that shaped the war's outcome. Germany had individual moments of organizational effectiveness. The V2 program demonstrated what concentrated effort could achieve. But these existed as exceptions, often dependent on individual leadership and isolated from broader scientific and industrial communities. The dominant pattern was fragmentation, duplication of effort, competition for resources, and subordination of scientific judgment to ideological or political considerations. Werner Hartmann, examining the SCR-584 in that farmhouse barn, was looking at the physical manifestation of these organizational differences. The clean circuit layouts, the standardized components, the elegant integration of subsystems, all of this spoke to a development process that was methodical, collaborative, and adequately resourced. It was the product of a system that worked, created by people who were free to focus on technical problems without political interference, supported by an industrial base that could translate designs into hardware at scale.
The SCR-584 served throughout the remainder of World War II and beyond, seeing action in Korea and remaining in service with various militaries into the 1960s. Its technological descendants, automated tracking radars with digital computers replacing analog circuits, remain fundamental to air defense systems today. The principles it embodied, automated target tracking, integrated fire control, continuous position updating, have become so standard that modern air defense systems are essentially descendants of the philosophy it pioneered. But the system's historical significance transcends its technical specifications or operational record. It stands as evidence of a particular moment when American scientific and industrial organization demonstrated superiority not through individual genius, but through systematic effectiveness. It represents a validation of democratic approaches to technological development, collaborative, pragmatic, transparent, responsive to feedback, over authoritarian approaches that prioritized hierarchy, secrecy, and ideological conformity.
Werner Hartmann spent the last decades of his career working in an organizational environment that consciously modeled itself on the American approach he had first encountered through examining captured equipment. The post-war German electronics industry, like those of Japan and other former Axis powers, adopted systems engineering methodologies, collaborative research models, and integration of academic and industrial development. The success of these approaches in creating prosperous, technologically advanced societies in the decades following the war stands as perhaps the ultimate validation of the principles the SCR-584 represented. When Hartmann passed away in 1979, his obituary in German technical journals mentioned his wartime service only briefly, focusing instead on his contributions to post-war radar development and his role in training a new generation of German engineers. But those who knew him well understood that his most important lesson had been learned in March 1945, examining American equipment in a farmhouse barn as his country collapsed around him. He had learned that technical excellence without effective organization is insufficient, that individual brilliance without collaborative structure is wasteful, that the most sophisticated solution built in small numbers will be defeated by the adequate solution built at scale. The SCR-584 sat in that barn, mud-spattered and ordinary-looking, its secrets gradually revealed through careful examination. And in those secrets lay not just the technical details of microwave radar and servo control systems, but a deeper lesson about how free societies organize knowledge, how democratic institutions enable innovation, and how the integration of science, industry, and purpose can create capabilities that exceed the sum of individual talents. Hartmann turned the system on, and the dish antenna rotated smoothly, searching the sky for targets that in March 1945 filled the German heavens in numbers that made defense futile. The quiet hum of the radar spoke of certainty, of mathematical precision, of automated response. It was the sound of the future, and it belonged to those who had built systems, not just components.